Hello students, welcome back to Golu ki Paathshaala, your favorite learning destination where science becomes super easy and super interesting. Have you ever wondered, why do we need to maintain distance from the vehicle ahead? Why does a football keep moving after being kicked? Why do we feel a force when sitting on a merry-go-round? Well, all these questions are connected to one fascinating topic, motion. In today's chapter, describing motion around us, we will learn how scientists describe motion using distance, displacement, speed, velocity, acceleration, graphs and equations. Don't worry if these terms sound difficult right now. By the end of this video, you'll understand every concept in the easiest possible language. So grab your notebook, stay till the end, and let's begin our journey into the amazing world of motion. Look around yourself. A train moving on a straight track. A car moving on a straight highway. A ball falling vertically downward. An athlete running on a straight track. All these are examples of motion in a straight line, also called linear motion. Before studying motion, we first need to know where an object is located. This brings us to the concept of position. Imagine your friend asks, "Where are you?" Can you simply say, "I am here"? No, you need a reference point. For example, I am 100 meters away from the school gate. The school gate becomes the reference point. A reference point is a fixed point used to describe the position of an object. To describe position, we need distance from reference point, direction from reference point. If an object's position changes with time, it is said to be in motion. If the position does not change with time, it is said to be at rest. It is important to note that motion and rest are always described with respect to a reference point. Now, let's clear up a common point of confusion. An instant of time and a time interval are actually not the same thing. An instant of time is a single, specific snapshot. It's just a single reading on a clock at a given moment, like looking at your watch and seeing exactly 10:05 am. On the other hand, a time interval is a duration. It's the actual gap or span of time between two different instants. For example, the 2 minutes it takes for a car to travel from start to finish. So, remember, an instant is a single clock reading, but an interval is the time duration between two readings. Ready to go a step beyond? Let's look at how we measure things in physics. Physical quantities are actually divided into two main types, scalars and vectors. First, we have scalars. These are quantities that are completely described by just a numerical value or magnitude. Think of things like mass, temperature, or time. You don't need a direction to say it's 5 kilograms or 37 degrees Celsius. But then we have vectors. These are quantities that require specifying both a magnitude and a clear direction. For example, force or velocity. It's not just how fast you are moving, but where you are headed. You'll dive much deeper into these concepts in higher grades, but for now, remember, scalars only have value, while vectors have value in direction. Now that we know how to describe position, let's put it into practice. What happens when an object actually moves? To understand a journey, we have to look at two key concepts: total distance traveled versus the magnitude of displacement. Let's track our athlete's path to see how they work. Let's look at this example together. Suppose our athlete starts right here at point O at time t equals 0 seconds. She runs forward, reaching point B at 4 seconds, and keeps sprinting all the way to point A at 10 seconds. At this point, she has covered a straight line of 100 meters. But she doesn't stop there. From point A, she turns around and runs back along the exact same path, stopping at point B at 16 seconds. This return journey from A to B is another 60 meters. So, how much is the total distance traveled? Distance simply cares about the entire path length. We just add them up. 100 meters forward plus 60 meters back gives us a total of 160 meters. Now, what about her displacement? Displacement only cares about the shortest gap between where she started and where she stopped. Since she started at O and finally stopped at B, we look at the distance OB, which is just 40 meters. See the difference? Total distance is 160 meters, but the actual displacement is only 40 meters. This is exactly why distance is a scalar, and displacement is a vector. Now let's understand two very important concepts. Distance and displacement. Distance is the total path covered by an object during motion. Suppose an athlete starts from point O, runs to point A, and then comes back partially to point B. The total path covered is called distance. Distance only tells us how much path was traveled. It does not care about direction. Therefore, distance is a scalar quantity, and its SI unit is meter, denoted by m. Displacement means the shortest straight line distance between initial and final position along with direction. Suppose you walk around your school and finally reach the same place from where you started. Distance traveled may be large, but displacement becomes zero, because your initial and final positions are the same. Therefore, displacement depends only on starting and ending points. It has both magnitude and direction. SI unit is meter, denoted by m, and it is a vector quantity. Before we move ahead, let's look at the difference between distance and displacement. While they sound similar, they play by completely different rules in physics. Let's look at the crucial differences you need to know. Distance can never be negative. It only adds up with every step you take. Displacement is flexible, it can be positive, negative, or even zero if you end up back at your starting point. Because distance counts the whole path and displacement is just a shortcut, distance is always greater than or equal to displacement. The magnitude of displacement can never exceed the total distance. Keep this cheat sheet in mind, and you'll never get confused by numericals. Let's jump straight into the next topic. Activity 4.1 of the ball thrown upwards. Imagine a ball thrown vertically upward. As it rises and comes back to the starting point, distance keeps increasing. But when it returns to the starting point, displacement becomes zero. This activity proves that distance and displacement are not always equal. They become equal only when motion happens in one direction without turning back. Now that we know how far an object moves, we need to know how fast it moves. The first concept is average speed. Average speed tells us how quickly distance is covered. Formula of average speed is total distance traveled divided by total time taken. Speed only has magnitude and no direction. Therefore, speed is a scalar quantity. SI unit of average speed is meter or m by s. Uniform motion. If an object covers equal distances in equal intervals of time, it is called uniform motion. Example, a train moving at a constant speed. While on the other hand, if an object covers unequal distances in equal intervals of time, it is called non-uniform motion. Example, a car moving in city traffic. Did you know that the science of motion didn't just start in a modern textbook? Centuries before modern physicists formalized the formulas, ancient Indian scholars were already decoding how things move through space and time. Way back in the 5th century CE, Aryabhat's famous treatise, the Aryabhatiya, laid down the groundwork for understanding planetary speed and calculations. Later, in the 14th century, texts like the Ganitikaumudi used these exact principles to solve complex mathematical word problems about distance and speed. So, every time you use the formula speed is equal to distance divided by time, you are practicing an ancient scientific legacy. The next topic is average velocity. Speed tells us only how fast an object is moving. But what if we also want direction? For that we use velocity. Formula of average velocity is equal to displacement divided by time taken. Velocity tells how fast and in which direction. Therefore, velocity is a vector quantity. SI unit of velocity is m by s. Ever looked at your car's speedometer and thought, yep, that's my velocity? Well, close, but not quite. Think of it this way, your speedometer tells you how fast you are going at that exact split second. That's nearly the exact magnitude of your velocity. But velocity is a team effort, it also needs a direction. And where do we get that? Look down at your tires. The direction your wheels are pointing gives you the direction of your travel at that precise moment. Put the speedometer and the tires together, and boom, you got your true instantaneous velocity. Now let's move to another important concept. Acceleration. Suppose you're sitting in a bus. The bus suddenly starts moving. You feel pushed backward. When the bus suddenly stops, you move forward. Why? Because the velocity is changing. Acceleration tells us how quickly velocity changes. Formula of average acceleration is EUAL to change in velocity divided by time taken. SI unit is m by s square. Now, let's look at the two sides of the same coin. Positive and negative acceleration. First up, we have positive acceleration. This happens whenever an object's velocity increases. Think about riding a bicycle. The moment you pedal harder and start speeding up down the street, you are experiencing positive acceleration. But what happens when things slow down? That's where negative acceleration comes in, often called retardation or deceleration. This is when velocity decreases. The perfect example is pushing down on your car or bike brakes to smoothly come to a halt. So remember, speeding up is positive, slowing down is negative, but both mean your velocity is changing. Here is a mind-bending question for you. Can an object be moving incredibly fast, but have zero acceleration? The answer is a definitely yes. You see, acceleration doesn't care about how fast you are moving. It only cares about how quickly your velocity is changing. If your velocity isn't changing, your acceleration is completely flatlined at zero. Think about a bus cruising down a perfectly straight highway at a steady 100 km prati ghanta. It's moving fast, right? But because it's traveling at a constant velocity in a straight line, there is absolutely zero change in speed or direction. No change in velocity means zero acceleration. So remember this very important point. A fast-moving object can absolutely have zero acceleration. It's not about the speed, it's all about the change. Drop an object, and what happens? It falls. But it doesn't just fall at a steady speed, it actually gets faster and faster every single second it's in the air. This constant speeding up is caused by a very specific force called Earth's gravity. And the acceleration produced by this pull has a special name. We call it acceleration due to gravity. In physics, we give it the symbol g. And on Earth, its average value is a constant 9.8 meters square. This means that for every second an object is in free fall, its velocity increases by about 9.8 meters per second. Now, which way does it point? Because gravity pulls everything toward the center of the planet, this acceleration always acts downward, straight toward the Earth. Since the object is speeding up in the exact same direction it's moving, the acceleration is in the direction of motion. So, whether it's a dropped phone or a falling skydiver, remember, g is equal to 9.8 meters per second, and it's always pulling down. And with that, we have successfully unlocked the first half of Chapter 4, Motion. Before we end this video, let's do a quick revision of everything we've learned today. We started by understanding what motion is and learned that an object is said to be in motion when its position changes with time with respect to a reference point. Then we explored the difference between distance and displacement. We learned that distance is the total path traveled, while displacement is the shortest straight line distance between the initial and final positions, along with direction. After that, we understood average speed and average velocity. Remember, speed tells us how fast an object moves, whereas velocity tells us how fast and in which direction it moves. Next, we discussed uniform motion and non-uniform motion, and saw how objects can move either at a constant speed or with changing speed. Finally, we learned about average acceleration, which tells us how quickly the velocity of an object changes with time. We also understood the concepts of positive acceleration, negative acceleration or retardation, and acceleration due to gravity. And with that, we've successfully completed part 1 of this fascinating chapter. But wait, the story of motion doesn't end here. In part 2, we'll learn how scientists use graphs to represent motion, understand position time graphs, velocity time graphs, learn how to calculate acceleration using slope, displacement using area under the graph, and finally master the kinematic equations of motion, which are extremely important for exams and numericals. So make sure you don't miss it. If this video helped you understand physics in the easiest way, then please give this video a big thumbs up, share it with your friends who are studying in class 9, and if you haven't joined our learning family yet, subscribe to Golu Ki Paathshaala and press the bell icon so you'll be the first to watch part 2 as soon as it's uploaded. Thank you so much for watching. Until then, keep learning, keep asking questions, and always remember, physics becomes easy when you learn with Golu Ki Paathshaala. See you very soon in part 2. Bye everyone.